Welcome back to Wiser Quantum 2025 program. Today we have a very exciting session planned for you. In fact, two very exciting sessions planned for you. First, we'll be having Dr. Korbinian Kottmann from Xanadu. He is interested in quantum simulation, does a lot of open source quantum software, and Xanadu is involved in software-driven research that feeds directly into research driving PennyLane. But yeah, Dr. Korbinian is here today to talk about a very exciting topic. Another fun fact about him, which maybe you all should also be aware of, he's an excellent karaoke singer. So if you ever get a chance to meet him at some conferences or at some site visits, definitely catch up with him. Over to you, Dr. Korbinian.
Thank you for that kind introduction, and thank you for having me. Today's topic is going to be quantum simulation and Lie theory. Lie theory has been a topic that is very closely connected to quantum mechanics ever since its origins. If you read old high energy physics papers or any high energy physics paper, Lie theory plays a big role. But it's not been so super common or so widespread in quantum computing or quantum simulation. And that recently has changed again. There's been some papers that use Lie theory. And yeah, I want to give basically a brief introduction to Lie theory and how it's connected to quantum computing, quantum simulation, and all that buzz. Before getting into that, a little advertisement. So most of the stuff that I'm going to talk about is kind of independent of PennyLane. PennyLane is the open source software that we're developing like Xanadu. It's quantum computing software built by researchers for research. And a lot of the things that I'm going to talk about you can do in PennyLane. And there's eventually going to be some small code examples or even some bigger, what we call demonstrations. And those are also I mean, I think this is one of the biggest driving factors for people to use PennyLane, because these are great resources for to learn about mathematical physical concepts, and on the other hand, learn about coding and directly implement the mathematical and physical concepts in code. And the nice thing about these demonstrations is that they're continuously updated, so you should never have the problem that you're trying to run a demo and it's not working because you have the wrong version. As long as you're on the latest version, they should run. Maybe there are a few exceptions, but for I would say like 99% of the demos, this should actually be the case. Yeah, so the outline for today's talk is I'm gonna basically introduce what is Lie theory. And you don't need to be scared if you're somewhat familiar with quantum computing. Most of the objects that I'm going to talk about, you already know. I'm just going to give them a slightly different name, and we're going to do some tricks with them. And then we're going to see some examples in how Lie theory plays into quantum computing or quantum simulation. So our first kind of, yeah, we can call it an application, is classical simulation, also quantum simulation and quantum compilation. And yeah, what these entail in detail, we're gonna see in a brief minute. Also, I talked about this with her. If you have any questions, if you feel lost at some point during the talk, actually feel free to just speak up or ask the question. I'd rather interrupt for a brief second and have everyone on board than, I don't know, go over something too quickly and lose half the audience. All right, so Lie theory one-on-one. All of the contents that I'm going to talk about today, they're essentially an accumulation of various demos that I wrote. So I'm going to put the demo title in front of the sections. So you can, if you want to know more about these things or just kind of revisit what I talked about afterwards, this is where you can find them, PennyLane AI/demos or PennyLane.ai/q/demonstrations. So Lie theory one-on-one. In quantum computing, we're all familiar with gates and with unitary circuits. So these are the fundamental building blocks of quantum computing, unitary circuits. And a unitary operator is defined by the fact that the inverse of a unitary operator is just its adjoint. This is also why sometimes quantum computing is referred to as reversible computing, because all of the quantum circuits that you're doing, when they're unitary, you can reverse them by just taking their adjoint. On the other hand, typically at the end of a quantum circuit, you want to measure some observable, typically encoded in some Hamiltonian. And those Hamiltonians or observables, they are made up of Hermitian operators. And Hermitian operators, they're defined by the fact that the adjoint of an operator is equal to the operator itself. This has some mathematical implications like the eigenvalues being real. And that is one of the reasons why they're describing observables, because all of the observable outcomes, measurement outcomes, are real numbers. Now, if you know these mathematical concepts and these mathematical objects, you're already pretty familiar with Lie theory, because the unitary matrices and the Hermitian matrices, they make up the corresponding Lie group and Lie algebra that are relevant for quantum computing. And they're both related with each other via the exponential map. You can view it anything that's in the exponent. This is describing the algebra, and everything that's on the bottom, so to say, is making up the group. And you probably already at some point heard about the Pauli operators. They're in some way a bit special because they are both Hermitian and unitary. So sometimes we see Pauli operators appearing in the exponent, and then we can view them as elements of an algebra, or we can see them at the quote unquote bottom and view them as group elements. Now, let me tell you what is actually the group and the algebra that I'm talking about. So it's sometimes when you're in this picture, sometimes it's sometimes more easy to reason about a quantum circuit or some concept in quantum computing when talking about the algebra, and sometimes it's more convenient to talk about it on the group level. Often it is, handy to talk about it on the algebra level. So let me tell you firsthand what is the definition. So a Lie algebra G, so this Fraktur G, is a vector space equipped with a commutator. And importantly, usually when we talk about vector spaces, for example, Hilbert space, we talk about wave functions, so really vectors. In this case, the vector space refers to objects that are made up of operators. So operators themselves can also form vector spaces. Yeah, and the vector space that we're talking about here is the vector space of linear operators. And sometimes they're unitary and sometimes they're Hermitian. No, they're Hermitian. And to make this vector space a Lie algebra, we need the commutator. In principle, this concept of Lie algebra is more general than just with commutators, but for all practical purposes in quantum computing, we only care about the case where this is the commutator. And an important property is that when you have a Lie algebra, it needs to be closed under the commutator. That means any element from your Lie algebra that you're taking, and you take the commutator with another element, you should get a new element that is again in the Lie algebra. So you can never escape the Lie algebra via the commutator. So for example, let's take the Pauli operators x and y. Together, they don't make up a Lie algebra, because if you take the commutator between x and y, you get a new operator z, so the Pauli operator z, and that one is not in your original algebra. So these two operators alone, they do not form a Lie algebra. But what you can do is you can perform the Lie closure. And sometimes the Lie closure is just an abstract mathematical concept where you say, oh, I have these operators that I care about, and in order to reason about them on a Lie-algebraic level, I'm just doing the Lie closure without ever computing it, or you can actually go and compute it. In this case, it's pretty simple. We can just add the Z operator and we're done. But in some cases, it's more complicated, and we do have software tools to help you do that automatically, so you don't have to do it by hand. I mean, this example is pretty straightforward, but imagine you have some larger operators that are a bit more complicated. Then you probably don't want to do it by hand, and it's neat to have software tools helping us do it. All right, yeah. So this is essentially a Lie algebra. It's a bunch of operators. The concepts are more general than that, but for all practical purposes, just think of it as Pauli operators. So Pauli operators like tensor product with each other and sums of them. These are the Lie algebras that we typically care about. They're composed of these elements. And in order for them to be actual Lie algebras, we need to close them via the Lie closure. And yeah, this is pretty much it already. So I think Pauli operators is pretty common in quantum computing. Commutators is pretty common in quantum computing. And we're just using the same objects and we're giving it new names and say this is now a Lie algebra with this additional property that we're giving it, that it's closed under the commutation. All right, so imagine you have some quantum circuit. So each of these boxes is a unitary gate, and each of these unitary gates, they're generated by some Pauli operator. So in that case, we have like Pauli operator XX. These numbers, oh, I messed up the indices. Well, there should be just XX, XX on the appropriate wires, and the Z operators. So yeah, this is a circuit, and we can look at the gates that are generating that circuit, and we can look at the operators in the exponents that generate these gates, and we can compute their Lie algebra. Now again, as I told you before, the Lie group and the Lie algebra, they're connected via the exponential map. So the corresponding Lie group that this circuit is targeting or part of depends on the depth, how complete your mapping is, but it's a subset of all of the unitaries in this group G. So what I want to say is, by looking at these generators and computing the Lie closure, we can say something about how expressive is this quantum circuit. And in that case, if we look at those generators, they're forming the so-called special orthogonal group. And this is one of three important semi-simple Lie algebras that we typically encounter in quantum computing. So you just need to know these three. This is a unitary group. These are just general unitary matrices. There's an orthogonal group, or the orthogonal algebra, which is on the group level, it's the matrices that are orthogonal, so kind of a bit more special than unitary with just real matrices. And we have the symplectic, which is a bit more niche, I would say. So maybe you've seen it, maybe not. I think don't care about these things too much. This is just to say, by looking at the generators and by looking at the Lie closure of these generators, we can say something about what group this unitary circuit is mapping to. And yeah, this is at this point, very general statement, and doesn't have too many practical implications yet, but we're going to see some applications for Lie theory and a bit more theory while we go there. So first of all, I want to talk about a classical simulation method. Let me give the spoiler already at this point that this simulation method, it's not too practical, in the sense that there's very rarely an application where you can actually use this and this scales, but it has some important theoretical implications, in particular for Barren plateaus. But this is just a spoiler. Let us walk there step by step. Again, this is the contents that I'm going to show you now. They're basically taken from this demo that I wrote. So if you want to know more details, feel free to check it out. Okay, so again, we're in the setting where we have some operators that are forming a Lie algebra. And a very important concept in these Lie algebras are the so-called structure constants. You can view structure constants as the coefficients of decompositions of any possible commutator that you can take. And with that knowledge, the structure constants themselves, they're a full and faithful description of the Lie algebras that we're looking at. Think of it like this. On the left-hand side, we have some operator, and on the right-hand side, we have some coefficients times, again, some basis of those operators. So this is just a linear decomposition of your left-hand side. And you do that for any possible combination of commutators, and then you get the so-called structure constants. Now, these structure constants, you can compute them by hand by just, I don't know, but basically by doing the linear decomposition. You just compute all possible commutators and then linearly decompose them and collect the coefficients. You can do that by hand, of course, but you can also do it in code. There's a function qml.structure constants on the Lie algebra that you're taking. Now, These structure constants, they inform what this identity actually doesn't have a name. This is just what I or we call it. We call it the adjoint identity. And the adjoint identity, it tells you how any of your operators from your Lie algebra evolves if you sandwich it from left to right with U and U dagger. And U and U dagger is again generated by some element of your Lie algebra. And when that is the case, you can rewrite that in terms of the exponential of some matrix, and that matrix is again the structure constants. Now, this left-hand side here, this is what is sometimes called capital adjoint action on the group level. And on the right-hand side, we have exponent minus I, the adjoint action with the lowercase on the algebra level. So this is why this is called the adjoint action. And this is one way. On the right-hand side, this is how you see it written on Wikipedia. And this is sometimes not so handy to use. And on the left-hand side, this is how, I don't know, you would encounter it in maybe in physics papers, like the GSIM paper. And then you can use it for the technique that I'm about to show you now. So importantly, kind of takeaway from this page is there are these structure constants. These structure constants completely describe our Lie algebra, and we can use that knowledge to inform how operators transform under group elements. Because that is essentially what is happening in a quantum circuit. Imagine you have some quantum circuit with, again, gates generated by these generators that some operators, for all practical purposes, think of them again as Pauli operators, so XX or just a Z or XYZ, could be whatever. Some Pauli operators, you take the Lie closure of them and they make up your Lie algebra. And now what you care about is you wanna in the end measure again these elements. They're Hermitian operators, so they're observables. You can measure them and you can compute the expectation value. And this is what you care about now. And we keep track of all possible expectation values for all of our Lie algebra elements. And we have some initial state rho 0 that we know a priori. Typically in quantum computing, our initial state is just a 0 state. It could be something else. Then we can compute all of these expectation values and we get some number and we put them in a vector. And that vector we call E for expectation value vector. Now, how does that expectation value vector transform under evolution of group elements from the corresponding Lie group? And that is exactly what the adjoint identity tells us, namely that all of these gates on the left-hand side, they correspond to some adjoint action. I put the adjoint identity on the bottom right so we can see them again. And so we see that any of these vectors in this trace, they just you essentially just multiply that vector with the adjoint identity, with the e to the I structure constants, which is the adjoint representation on the algebra level. I think that sounded way more complicated than it should have. The takeaway here is you have some vector of your expectations, and now the way that vector transforms is simply by some matrix multiplication. And that matrix multiplication is e to the I your structure constants. That is a takeaway. This is how this expectation vector of your initial values transforms. And now you might want to compute some expectation value of some observable that is a superposition with some coefficients here in the end. And then again, this is just a multiplication of yet another vector from the left. This technique is called GSIM, or Lie algebra simulation, or maybe you find other names for it. And the kind of cool thing about it is when we're doing classical simulations of quantum circuits or expectation values in quantum circuits, we typically work in a 2 to the n dimensional Hilbert space, and we need to keep track of that vector. And this is the reason why quantum computing is there, because we can't keep track of a 2 to the n vector for n larger than, I don't know, 30, 40, depending on how big your computational resources are. But it scales exponentially, so you're kind of stuck here. Now, GSIM tells us that we can perform all of this with matrices and vectors that are of the size of the dimension of your Lie algebra. So you might have a very large Hilbert space, but a small Lie algebra, and then you can perform GSIM on it. Again, the spoiler, this is rarely the case. But it does have some interesting theoretical implications because while all of this was developed, at the same time, people figured out that the Barren plateau problem. So this is kind of, I'm shifting gears here a bit. I'm going to a different topic, but they're related. The Barren plateau problem is in variational quantum algorithms, where it can happen that your loss function landscape becomes very flat. And so on average, when you initialize randomly, you will be somewhere where there's no gradient. So gradient descent doesn't work anymore, and your variational algorithm doesn't train, and then you run into a problem. And this is the so-called Barren plateau problem. And this is characterized by the expectation value. So like expectation here refers to averaging over different initializations of the gradient of your loss function and whether that scales polynomially or exponentially. And when it's exponential, we call it a Barren plateau. And now people have found out that this value, this expectation value of your gradient is inverse proportional to the dimension of your Lie algebra from your circuit. This was in a paper in 2023 entitled "A joint is all you need." I mean, the title is a bit longer, but that's a catchy phrase that you can Google later. And so what this tells us is that, that when the dimension of your Lie algebra is polynomial, you don't get Barren plateaus. And if it's exponential, you do get Barren plateaus. But this, on the other hand, earlier I told you that we have the simulation method that scales as the dimension of your Lie algebra. So that means when your dimension of your Lie algebra is polynomial, you can perform GSIM. When it's exponential, you get a Barren plateau. It doesn't work anymore. Now, there's been some debate about this, whether this means or implies that everything is doomed. I personally have the opinion that that is not the case. On one hand, GSIM almost never happens. Like these Lie algebras, you have to construct a very special Lie algebra to actually get something that is polynomial scaling. The vast majority of them are exponentially scaling. That means on one hand, it means we almost always have Barren plateaus, but Barren plateaus might not be the end of it. If you're initializing completely randomly, then Barren plateaus really are a problem. But if you have some more clever strategies and where to look, and typically in physics problems, you do have some initial bias on where to start your computation, you're not completely lost, and then you might not run into this problem. Another thing worth mentioning is that the GSIM is really only for expectation values. So it does not tell you anything about sampling, and a lot of quantum algorithms are about sampling. So you might have a polynomial scaling, some algorithm that has a polynomial scaling Lie algebra, and you are able to perform GSIM, but that only tells you something about expectation values and not necessarily about sampling. So you might still need a quantum computer to run that same algorithm doing sampling. Okay, this was a bit of a detour, but you can see how Lie algebras really are the central players in all of these debates that are kind of going on the last few years. So this has been kind of, I would say more concerned with classical simulation. Another interesting application of this, although this is actually not phrased like that, but if you look at the math, you can actually see it. You can perform essentially GSIM, but on a quantum computer. So this has been discussed in this paper here, archive 2407. I mean, you see the number, or you can just look at this demo. So the problem is quantum simulation as in time evolution. And what you're doing is you define some shadow state, and that shadow state is essentially the same as the vector we've seen earlier with the expectation values. So you encode all of the expectation values of potential elements, and you're encoding, you find what they call a shadow Hamiltonian. And this shadow Hamiltonian you get from your original Hamiltonian projected onto the basis of your Lie algebra. And then you can run a quantum circuit starting from this initial state. using this shadow Hamiltonian as an evolution and perform what they call shadow Hamiltonian simulation, which essentially is GSIM on a quantum computer. It's a bit funny because this is not your typical setup where in the end you have some expectation values. Your expectation values are now the amplitudes of your state. So this is a fundamentally different setup to how you typically do quantum computing and quantum simulation. It's an interesting use case. I'm actually not sure how practical this is, but to be honest, I genuinely don't know, so I don't have an opinion on this. But it exists, and it is related to Lie theory, and this is why it's worth mentioning here. Cool. So for the last bit, last 10 minutes, we're going to do Lie theory in quantum compilation. I'm not sure if quantum compilation is actually the correct term here. I'm just using it referring to the fact of translating something that is a classical description of some physical problem into something that we can run on a quantum computer. That is what I consider quantum compilation, and this is what these two demos or these two topics are about. So this is going to be split in two parts. In the first part, we're going to talk about the fixed depth Hamiltonian simulation via Cartan decomposition. And another very important concept in Lie theory. So earlier in GSIM, we saw the structure constants and we saw the adjoint representation. A new very important concept here is the so-called KAK decomposition, or sometimes also called Cartan decomposition. Technically, they're two different things, but sometimes the terminology is a bit used interchangeably. So first of all, a Cartan decomposition is you have some Lie algebra and you split that Lie algebra into a subalgebra. This letter here is very ugly and it's very hard to read. This is Fraktur K, so this is small k. And this small k is a subalgebra, meaning that when you take the commutator of elements from k with elements of k, you will get something that is again in k. And that is the definition of a subalgebra, sub-Lie algebra. And it has these additional curious properties, reductive property and symmetric property, meaning how the relationship between K and M. So K and M, they're orthogonal complements of each other, and they're not arbitrary orthogonal complements. They're done in a special way. If they're done in a special way that it fulfills these two properties, then we call this decomposition Cartan decomposition on the algebra level. Now we can further decompose the M part. M is not a subalgebra, and we can take a subalgebra of M, and a subalgebra of M has to be abelian. Abelian means that all elements, they commute with each other. This is a special subalgebra, like there's actually infinitely many of them. And this is what we call, like one of them we call a Cartan subalgebra. It's important because it informs the so-called KAK decomposition. On a Hamiltonian level, it means that you can write some Hamiltonian as some operator K, which is unitary, times another operator, which is again Hermitian, times again another operator, which is unitary again. These K elements, they're in the e to the I K. This is a subgroup because K is a subalgebra. And A is an element from this abelian subgroup. And we're gonna, in just one slide, see how we can utilize this for quantum compilation. I just want to mention that the kind of the Cartan decomposition or the KAK decomposition, this is now on the algebra level equivalent. We can also do this on the group level. Now consider the problem where we want to do time evolution of some Hamiltonian. I showed you earlier how we can decompose such a Hamiltonian as a KAK decomposition on the algebra level. We can do that. K1 and K2 are unitary, and we can split them apart and we get something that is called fast forwarding. This is called a fast forwarding because the K's, they're not dependent on T anymore. So any T you put here, this circuit always has the same depth because the only thing that you're changing is this parameter here. And this is why this whole thing is called a fast forwarding. Now, this, of course, it's almost like a cheat code. This is too good to be true. In the sense that, like, if we can always do that, we solve all of the problems in quantum computing that are related to time evolution, which is typically a problem that is not solved. It's something that is still ongoing research, and people look for the best ways how to write this as a circuit. So there is some caveat, and that caveat obviously is the dimension of all of these things. Because when these decompositions reach too large dimensions, and that dimension is again the dimension of your Lie algebra, you can't do anything anymore. So this whole setup, this fast forwarding, is restricted to settings where your operators have a small Lie algebra. This is still curious, I would say, because you can, so far, I think time evolution has been restricted to cases where you have few qubits, but you could now in principle have a system where you have a lot of qubits, but they're encoding a small Lie algebra, and now you can do this fast forwarding. Another way to think about it, when I talk with colleagues that are not familiar with these things, and they talk about fast forwarding, what they typically mean is this is something where we have an analytic solution. Now you can kind of extend this notion of fast forwarding to this is something where we have an analytic solution or the Lie algebra is small, and then we can also do it. Again, this is all explained in more detail in this demo. The second part of the quantum compilation bit that I want to show you is the question like of unitary synthesis. So think of the scenario where you have a quantum circuit given as a unitary matrix. So you're given a dense unitary matrix in terms of numbers of 2 to the n times 2 to the n. Now the question is, how do I translate that into a circuit? And this is the problem of unitary synthesis. And there are three kind of standard ways of doing that. Of course, up to some number of qubits, you can't do that arbitrarily large. But for some subcomponents, there's the quantum Shannon decomposition, the Carnesia-Glaser decomposition, and the block ZXX decomposition. The first two, they're rather old. They're like from, I think, the 2000s or 2010s. And the block ZXX is recent. It's like a small improvement. And it turns out that all of these can be uniformly described as Cartan decompositions, or rather recursive Cartan decompositions. There is a set of allowed Cartan decompositions that you can do. And the most typical way is when you start with some unitary, you can do a A3 decomposition, followed by, so in this A3 decomposition, you get a multiplexer of some, again, unitary gate with a smaller qubit count, some multiplexed qubit rotation, and again, the other K on the other side. And then you can further decompose this bit with an A decomposition. And now if you look closely, you're counting starting on the top left, you're starting with a U2 to the n, and you're finishing with a U to the n minus 1. So you can recursively repeat this procedure until you're left with just 2. So you just have a single qubit unitary. So you can give me a matrix that is a unitary of some 2 to the n times 2 to the n, and I can recursively decompose it using these two Cartan decompositions going further. Now, the quantum Shannon decomposition, Carnesia-Glaser, block ZXX, at some point they use slightly different choices to do some optimizations, but they're all in this framework of just recursive Cartan decompositions, which is new insights that some colleagues of mine found. We do have of course, there's a paper for it, but there's also a demo for it that you can check out. I think I'm good on time. Plan was something like 40 minutes. And with that, I want to conclude. Thank you for your attention. Honestly, this is the main takeaway that you should take away from this, namely that the objects that you're already familiar with, circuits being unitary matrices and observables being Hermitian matrices, they form the group, the Lie group and the Lie algebra respectively, and they're connected with the exponential map. And then there's all this stuff that I've briefly showed you that you can check out if you're more curious in the demos or in the respective papers. Yeah, and with that, thank you for your attention, and I'm happy to answer any questions that you have. I'm sure you have.